Alright everyone, welcome back to Cody's Lab. So if you watch my channel, you probably have some interest in science and space and stuff, so you will probably know that the Artemis 1 mission has launched and is on its way to the moon. Now this is a robotic mission, nobody's on board, but it is testing out everything for humans to be going back to the moon, which is extremely exciting. And today I wanted to talk about why I personally am excited for people to be going back to the moon. Those of you that have been following the channel for a long time will know that I studied geology in college. You also might know that I haven't actually graduated yet, nor have I taken the certification tests or actually worked in industry. So I can't actually call myself a geologist, but I do know some things about rocks and the stories that they can tell us. So what does the moon have in terms of rocks that the Earth doesn't? Well, the real question is, what does the moon not have? And that is an atmosphere to weather the rocks down. And as far as I know, it's never had plate tectonics to recycle the rocks into the surface and melt them. So everything that's happened to the moon since it has formed, since the surface has cooled, has been preserved. And what this does is it preserves a record that goes back a long time. The average rock that's on the moon is older than the oldest rocks on Earth, because the Earth just destroys everything. So, what I specifically will be talking about is actually the loose material, the regolith, that is blasted up by meteor impacts. So, and a meteor or asteroid, comet, whatever, strikes the moon, it's going to blow material up, and that material is going to then rain back down onto the surface of the moon. So the moon's original surface, which is essentially cooled lava, is going to get covered by layers of this blasted off regolith. And as these layers are being deposited, things are happening in the solar system, to the moon, and out in the galaxy. So the sun, for one, is going to be putting elements down, so hydrogen and helium mostly, from the sun. Is going to be trapped in those layers. And the different ratios of isotopes of these elements and the different amounts is going to tell us what the sun has been doing. Also, things outside of the solar system, like a supernova goes off, is going to also put material down in the layers. So the very top layer, if there's a supernova, nearby the Earth is going to send material such as iron, different isotopes of iron, down and embed it into the layers. Also, the irradiation is going to create new elements inside the rocks that make up the regolith, such as beryllium. And then after that happens, over time, more impacts will occur, more layers of regolith will be put down, and the record of that supernova or other events will be preserved. Now, how will we know how old each of these layers is? How will we know when this layer was put down, roughly when the supernova occurred? Now, of course, we'll know that the older layers will be on the bottom and the younger layers will be on top, but specifically how old each layer is, well, one way we can tell is through potassium-argon dating. So if you have a crystal of rock, such as feldspar, that contains potassium, that potassium, over time, specifically the potassium-40 isotope, is going to decay at a known rate into argon. And that argon, over time, is going to build up inside the crystal. It's a noble gas, it doesn't react with anything, but it can't get out of the crystal, so it's stuck there. But now, if we melt this crystal, say we have a asteroid come in, and the impact will create lots of heat from the compression that will actually melt some of the material and then shoot it out along with the pulverized material. And these little bits of melted rock, as they're flying, will form droplets which no longer can hold the argon. Especially in a vacuum, the liquid rock can't hold the argon, so the argon will leave the rock. The potassium, though, will remain. It's an earth element. It's very stable at high temperatures, so it'll stay behind. And then once this droplet cools again, it forms a chunk of essentially glass that we call a tektite, which contains the potassium, and then as the potassium decays, the argon will build up again, because the argon can't get out through the glass. By measuring the different ratio of potassium and argon, we'll be able to tell how old this little piece of glass is. Or rather, we'll know how long it's been since it was melted, because the melting process resets the potassium-argon clock. And those will be embedded inside of the layers. These layers are formed by impacts. Impacts create tektites, and so they'll be pretty common. They'll be all through it, and we'll be able to tell how old they are, and thus how old the layer that they are sitting in is. Now, once we know how old the layers are, we'll not only know when astronomical events have occurred, what the sun has been doing and stuff, but we'll also know about the impacts themselves. If we graph the age of each layer, you might have a pretty random mix, but you might also get some groupings of layers as time goes on. So when these groupings are occurring, you know that more impacts were happening. What would cause that? Maybe things that have happened out in space, like the orbits of the other planets have been changing. And there might be a pattern that arrives. We'll be able to tell maybe we're due for another storm of asteroids. Maybe a supernova occurred, and then a supernova layer happens, and then sometime later there's a bunch of impacts. Maybe the supernova caused something. Or maybe we'll get a bunch of these elements that look like the sun is putting out, but they're maybe isotopically a little bit different. And then we notice about the same time a bunch of impacts happen. Well, a star just flew near the solar system. And we might be able to, by knowing when that happened, be able to rewind things back and see which star that was. And therefore we have samples of elements from that star. There's so many other things that I just haven't included here that we can know from these layers. But what about the Artemis program that specifically excites me is the fact that the new spacecraft have more capability. They'll be able to go to the poles of the moon, or anywhere really, and not be limited to going to just the equator. So we'll be able to go to the north and south pole of the moon, places where the sun, the sun's rays coming in, never are able to hit. You see, the moon's axial tilt is very, very shallow. The Earth's axis is tilted like 24 degrees or so. The moon's is only tilted about 5 degrees relative to the plane of the solar system, which means those craters on the north and south pole of the moon never receive sunlight. And that means they're very cold and they're able to trap volatile materials. So when an asteroid or comet specifically strikes the moon, it's not only releasing a bunch of pulverized rock, but also it's releasing vaporized gases such as water, which are then able to fly out and become a temporary atmosphere of the moon. And like the dark side, they'll freeze down. So the water will freeze down as frost. Then as the moon rotates and the sun illuminates again, these materials will be vaporized and eventually will either get kicked off into space through random collision or gain enough energy from a photon, or they will find their way to one of these dark craters and get stuck permanently. And we know from a different spacecraft we've slammed into these craters that these craters do in fact contain lots of frozen water. Now, frozen water is exciting because you can make fuel, you can make oxygen for breathing. All sorts of stuff can be made from the volatiles that are there. And so you'll be able to use that as a fueling stop to go out farther into the solar system. But in these craters, you will have layers of ice intermixed with the layers of regolith. And ice tells you some things that rocks alone cannot. Specifically, we'll know what kind of asteroid or comet it was. Carbonaceous chondrite, M-class, L-class, and comets, they all have different isotope mixes because they came from different parts of the solar system. And so you might find that a grouping of your impacts were all comets that came out from the Oort cloud. That would indicate something happened out in the Oort cloud versus something that happened in the inner belt. Also, these layers will not just contain water ice. Now, of course, there will be water. Water will probably be the most common substance in these craters. But there's also going to be ammonia, NH3, methane, oxides of sulfur. So that ice is probably going to smell like gunpowder. Might have hydrogen sulfide also, so it might also smell like rotten eggs. It's also going to contain things like cyanide, which is poisonous, and mercury. Mercury might actually be a pretty common material to find because it's a heavy element. When it vaporizes, it's slow moving, so it'll remain caught by the moon's gravity, and it'll just collect places where it's cold enough to freeze it. But what's really interesting to me is these craters get down to around 40 Kelvin. That is cold enough to freeze nitrogen and oxygen. Compounds which you find in the Earth's atmosphere. The Earth's atmosphere gets thinner and thinner as you go up, but it never quite gets to zero. The Earth always has an atmosphere, and the moon's close enough to actually be within the Earth's upper atmosphere. And the sun actually, as the sun's rays come in, they'll actually kind of push on the upper atmosphere, so the Earth is going to end up looking kind of like a comet. And the material that gets blown off by the sun is about 100,000 tons of material a year. Now, 100,000 sounds like a lot, but the Earth's atmosphere weighs quintillions of tons, so it's a rate that you're not going to notice. But as the moon passes through this material that's being blown off from the sun, some of it will get stuck to the moon, especially in the cold areas, in those craters. Now, it won't be a lot of material. It'll be a very slow process, but over time, it will build up. The moon has been out there for billions of years, after all. And so what you're going to have is the impacts will throw up material. You'll have the ices that get put down from the impactor itself. But between that, you'll have the slow deposit of nitrogen and oxygen, water, sulfur dioxide, and other things that contain in the Earth's atmosphere that are collecting on the moon in those cold areas between the rock layers, the regolith layers. Now, it's probable that the heat coming up from the interior of the moon is going to melt and vaporize the lower layers, so we may lose some information. Also, when a lot of rock from a nearby impact rains down, it might vaporize large amounts of this volatile frozen atmosphere. But I think you might find places where there's enough of it to get a record of what's happened to the Earth's atmosphere over time. So for example, you'll have the oxygen isotopes like oxygen 16 and 18, and the different ratios of these oxygen isotopes will tell you what's been going on the Earth. If the Earth is snowballed, then the oxygen that's going to be in the atmosphere is going to have more of the oxygen 16, the lighter isotopes. If the Earth has a very high temperature, then you'll have a lot of oxygen 18 being able to get up to the moon. And the different nitrogen isotopes will also tell you some things. The carbon dioxide that's also trapped will be able to tell you what life itself has been doing. There's probably going to be methane trapped, sulfur dioxide if there's a big volcano or something, maybe an asteroid impact is going to release a lot of sulfur. Some of that sulfur is going to make it to the moon and end up in those layers of ice. Now, of course, determining whether CO2 that you find in a layer is from an asteroid impact like a carbonaceous chondrite, or if it came from the Earth, is probably going to be fairly difficult, but I don't think it's going to be impossible. It'll be intermixed with the nitrogen background that you have coming from the Earth, and also it'll be maybe distant from the dust and rock that you would expect to be kicked up by an asteroid impact, and also maybe the isotopic ratios will be unique to the Earth somehow. At any rate, people who are a lot smarter than me will probably be working on this problem. And if they are able to determine that the carbon dioxide has come from the Earth, well, this record might go back far enough that you might have carbon dioxide from the Earth's atmosphere back before photosynthetic life was making oxygen. Like, there might be layers that are so old that they no longer contain oxygen. It's just nitrogen and CO2. There would be no atomic oxygen because the Earth's atmosphere wasn't oxygenated yet. That's how far back the record is probably going to go. And the isotopes would be pristine because you actually have the material that came and landed on the moon. Here on the Earth, you might have a mineral that formed during that time, like the banded iron deposits, but we don't know for sure if the isotopes have been exchanged over time. We might have information that is lost. This would at least confirm information we've gotten from the rock layers on Earth and basically check ourselves to know whether or not we're right, whether or not they have been changed. And perhaps the record doesn't go back that far. Maybe something happened to the moon. Maybe at some point its axis of rotation was more angled towards the sun, so those craters were, had sunlight in them at some point, maybe 500 million years ago. Everything that was there got erased because the moon's orbit or rotation changed, wobbled on its axis. But that would be information that would be interesting still. That's something we don't know currently. And just tracking where the ice is inside the craters would be able to tell you everything about the wobble of the moon's rotation going back a very long time. And one more thing that would be interesting to go look at in those craters at the South Pole or the North Pole of the moon is alien artifacts. Now, I don't think it's likely that we're going to find alien artifacts. I don't think that aliens are common enough in the universe for us to have been visited. But if we have been, Earth is a very interesting target to look at. And that moon is a very attractive fueling spot. You would go, if you were an alien, to those areas to mine up some material and fuel up your spacecraft. Same reason that Earth's humans are going to go to those locations. if I'm an alien coming and studying the Earth, going and looking at one of those craters would be a way to get information from a long period of time before I got there. So there might be alien artifacts hidden deep in the shadows of those craters, and we haven't seen them yet. Again, I don't think it's likely that they're there, but I also think it might be worth having a good look just to see. And if not technological evidence for aliens, there might be bacteria or viruses that drifted in from interstellar space or Mars that landed in these super cold regions, which would preserve them perfectly for millions or billions of years. Certainly there would be viruses and bacteria drifting up from the Earth that would be captured, so we might be having samples of DNA from organisms, certainly from the Earth, that go back billions of years, which we don't have on the Earth because the fossilization process does not preserve DNA. So yeah, there's all kinds of information that could be locked within these icy layers. And I haven't even covered the majority of it probably. So I really hope that NASA, China, SpaceX, whoever, before they start strip mining and destroying all this information, that they at least take good samples and do all this science and write everything down and share the knowledge before it is destroyed. Because going to the moon's north or south pole with the intent of mining it for fuel is kind of like going to a forest of really old trees, like the bristlecone pines, and being excited for the trip because you don't have to carry the firewood because there's trees around you can cut down. It's like, yes, that is technically true, but cutting down those trees is going to destroy a lot of records in those tree rings and stuff, So don't burn your information before you gather it and preserve it in some other way. So anyway, that's what I'm thinking about right now. There's, of course, other things, different sources of science we can have other than just the stuff that's in the ice layers. And I hope that I've at least gotten you excited about it as well. Hope you enjoyed my little video. I'll see you next time.